who is visiting of physics and astronomy at McMaster University in Canada. He is a theorist, and his research is actually studying God and focuses on the interface between ultra-cold atoms and quantum optics and condensed matter physics. So it's a very, very interesting field of research. He has worked, for example, a lot on dipolar BCs, on cavity QED, and also on quantum catastrophes, which he's going to tell us more about today, in coupled BCs and spin chains and all these things. Duncan has actually worked with a number of quite famous people. So, for example, from 1994 to 1998, he got his PhD with Sir Michael Berry at the University of Bristol. And this is the Berry from the Berry phase.
Yep, that's the one.
Interestingly, he has also done a lot of hydrodynamics works and solitons and all these. So, yeah, so Berry is actually a very famous person. He's also an FRS fellow of the Royal Society. Then he went on, Duncan went on to the Weizmann Institute of Science, working in quantum optics.
Is that working now?
And enable your video.
Enable my video. How about that?
Yes, there we go.
Okay, great.
Sorry about it today, everyone.
Okay, so I work at McMaster University, which is about an hour outside of Toronto. So if you're ever passing through Toronto area, let me know. Be happy to show you around. All right. Oh, so this picture isn't just a random choice. What you'll see on the bottom of the swimming pool here is something you may have seen before, which are caustics. Okay, so these are these bright lines of light, where the light is focused by so sunlight is focused by these waves on the surface of the pool, and of course it's not perfect focusing like you learn about in an optics class. It's an example of natural focusing. Okay, and that's going to play a big role in what I'm going to say. I think this will stop working, but that doesn't matter. Let's try this. It's not working. Okay, I have a freeze.
One more click.
One more click, I think. Okay. That one went down. Okay, so in case, as I'll probably run out of time, here are my students that did the work. We're going to hear a lot about work by Wyatt here, who's now a postdoc in Heidelberg. And one of the students I started this work off with is Jesse, and Jesse's at Oklahoma State University at the moment, but he's moving to the University of Victoria, which isn't so far away from this part of the world. So he'll be moving there in a few months. Let's see if the next slide will click. Ah, yes. Okay. So natural focusing, we might think of it as something that occurs with light, and that's probably one of the best known example. So a rainbow is a situation where you have sunlight that is focused by raindrops in the air, but it's not perfect focusing, of course, because raindrops are not perfect lenses. But it's an everyday example of natural focusing that we're familiar with. A maybe slightly less everyday example is gravitational lensing. So I won't do it, but if you line up sort of A with A and B with B and so on, C, D, E, what you have is 5 different images of a distant galaxy that's the light's coming from that distant galaxy, but it's getting to Earth across, it's passing through space. And the light from that distant galaxy is that the light waves are distorted as they pass through space and get focused, naturally focused. And this would be one way to detect dark matter through things like gravitational lensing, micro lensing, and so on. And so you have to try and interpret. You want to learn something about what's between us and the source of light by looking at these natural focusing events. Another example is here the large-scale structure of the universe. So it's not universally agreed, but there are theories that say the large-scale structure of the universe is this very sort of supposed, it's not something we can easily see, but it's this sort of spider web of matter. So now we're talking about matter, not light. And the idea is that if you have a uniform distribution of matter and it's pulled together by gravity, then generically, and all these things are generic, that's part of the point, it will form this kind of structure. And these are, again, examples of what are called caustics. So caustic means to burn. It's from the Greek to burn, like caustic soda. And it's whenever you have some focusing effect, you get a very bright, in terms of light, you get very bright patterns. Another example is the twinkling of starlight. So why does starlight twinkle? Well, as the light passes through our atmosphere, the atmosphere presents a sort of random turbulent medium, which this is refractive index that the light feels, and it randomly focuses the light, and that's why the stars twinkle. Another example is freak waves on the ocean that do a lot of damage to shipping. They're either ocean currents or the topography on the bottom of the seabed can have the effect of focusing waves. I mean, it's not fully, it's a very complicated subject, real hydrodynamics there, but there's one of these effects. You can understand at least a fraction of them in terms of these same ideas as caustics. And finally, the example I show here is a tidal bore. So that's where you have an estuary, a river that sort of empties into the sea. And if it's a funnel-shaped estuary and you have a place with a high tide, then during the day, as the tide comes in, you get all this water gets focused into this river mouth, and you get a shock wave that shoots up the river going upstream. The water might be flowing down, but this is going upstream, and you get this case of an undular tidal bore here. And this is also an example of natural focusing. So I'll explain more why in some of these subsequent slides. Okay, so this is perhaps the canonical example of natural focusing, the rainbow. So imagine you have a single drop of water, and I've drawn it as a sphere here. It needn't be a sphere, that's going to be part of the point, but it should be roughly spherical. And so if I'm standing over here, I don't know if the camera still, maybe I can't stand over there, but if the sunlight's coming over my shoulder from the sun, and I'm looking up, there's a particular angle at which I will see a rainbow, which is about 42 degrees. And so what's happening is the light enters the raindrop, it refracts, then it reflects. So here I'm showing a single ray, and then it refracts again and exits. Okay, and so this ray is uniquely defined by where it enters the raindrop, this angle S. And then there's a second angle, so there's a small letter S. There's a second letter here, which is in capitals, which is the scattering angle. So this one I can choose. I can choose which angle to stick my head at. It's called a control parameter. And I'll see that as a function of angle, I'll see a rainbow or I don't see a rainbow. There'll be a particular bright direction in angle space. So if you plot, so here's a picture of many, or at least the top half of the drop illuminated by rays and looking at where they go. When you have many rays, you can explore what happens as you change this input angle, okay? As you change this input angle, they all come out at slightly different output angles. And what's plotted here is an input output. So the input is labeled by this S angle, which labels where the ray comes in. C is the output angle. And you can see an interesting thing with this curve. So as you change S, notice that it turns over at a particular, so there's a certain value of S here where all the rays come out with the same angle because it's locally flat, this curve here, and that's at 138 degrees, which is 42 degrees if I subtract it from 180. And so this is an example of focusing, okay? All these rays, a whole bunch of, if you're down here, a particular input ray comes out of a particular output. But if you have a bunch of rays around this turning point, they all come out with the same angle, 138. That's focusing, and that's where the rainbow comes from. That's the simplest example. Who's seen this shape in their coffee cup? Okay, some observant people, all, I hope at least the experimentalists have spotted this. So this is light. Imagine light now coming from above, as shown here, these parallel rays, and they're bouncing off the back wall of the coffee cup. And if this was a perfect parabolic mirror here, they would focus to a point. That's what we might learn in an optics class. But they don't, because this is a circle. Okay, it's not a parabola, and so it's not a perfect lens. And in fact, a focus point is unstable to any aberrations. And so it turns out that this focus point will explode generically into this cusp shape here, which is the envelope of these rays, and that's the brightest part of the pattern. And this now is stable. So if this was a plastic cup, this isn't one of those, but if I could press in on the sides, I would see that this shape gets distorted, gets stretched and sheared, but it still maintains its basic cusp shape. So this structure is stable against perturbations. You may, if anyone still irons their shirts, I know I don't, but if you did, you may notice that the creases meet. If I was to flatten this down with an iron, these folds will meet generically at cusp points. So that's what's shown here. Sorry, this is twisted to what's shown here, but this is the cusp tip here. And we can understand what's going on a little bit. So these rays are, you may know that what governs optics is something called Fermat's principle and principle of least time. We can calculate potentials that describe, which is the optical distance of these as the light passes through this sort of optical system. What you find is the minima here are the classical solutions, the ray solutions. What you find at any point inside the cusp or inside down here, there are three solutions. There's three turning points, and one there, and one in the middle here. But when you cross this boundary, two of them annihilate. You just have one outside, so a single ray anywhere outside. So what's happening in focusing is two rays coalesce on this point, and there's only a single ray outside. You can describe them via these potentials. Any of you that are into condensed matter might recognize these kind of quartic potentials from Landau theory, and there is a connection, which maybe we'll get onto. Okay, so caustics, these things, the rainbow, the fold, and the cusp, they have the property of structural stability. So they're stable against perturbations. And anything that's stable against perturbations doesn't need fine tuning. And that means it occurs generically in nature. And I like things that occur generically in nature. It means they're worth studying. So here's a remarkable fact, okay, that isn't often taught. It probably should be taught more often, that these structurally stable singularities only take on certain shapes. So this is a very sort of pictorial subject. In one dimension, it's a point. So like in this rainbow, we had this particular point in angle space, one-dimensional angle space. The cusp is the structurally stable singularity in two dimensions. So why is this is a singularity? Because that's the brightest part of the pattern. If you do the ray theory in that coffee cup, you'd find that the intensity formally diverges along this cusp shape. As you go into higher dimensions, there's three of them, three different structurally stable shapes, and you can't smoothly deform one of these into any of the others. So they're sort of independent shapes. So these things were figured out by mathematicians, by topologists, René Thom, a French mathematician, and Vladimir Arnold, a Russian mathematician. But each of these surfaces is a bifurcation. It's where the number of rays, the number of classical solutions to your problem changes. So for instance, 2 of them merge as you cross this line, whereas 3 of them merge right at the very brightest point at this special point here. And so it goes. And you can also see the higher ones contain the lower ones. So this line here is like a rib made of, imagine translating this cusp and so on. So the higher catastrophes contain the lower ones. So this is a very remarkable and very strong mathematical result that tells us that there's something universal about singularities, that they can only take these certain shapes, at least generically, they only take these certain shapes. So there's a bit of mathematics, there's some nice pictures and some nice mathematics, but you can describe each of these structures by the set of polynomials here, which are called generating functions. So you might recognize this, the little letter s. Remember, that was the angle at which the ray entered the rainbow. So actually, this one is the rainbow up here. And the control parameter c, that was the angle at which we were putting our head. So these, you can describe these things mathematically in terms of a generating function. It's the optical distance in optics, or the action if we're talking about mechanics. And so if you take the derivative of this thing with respect to s, that's your principle of stationary action. If you solve the equation, you say, where is this function stationary? Where does it have its stationary points? You take the derivative, set it equal to 0. That gives you your classical solutions. So you can see that, for instance, this one, when you take the derivative, will have 2 solutions. When you take the derivative of this little cubic, and the rainbow is exactly where 2 of them will merge. And they're all described by these polynomials. Let's show, okay. So much for the ray theory. Okay, that was the ray theory. How about, so if we have a singularity in the ray theory, a general principle with singularities is I don't like them. I like to resolve singularities. Usually there's some extra degree of freedom which you have to introduce into your theory which will remove a singularity. Now in optics we know and have known for a few hundred years what that is, and that's phase, the idea of introducing phase. So, and that allows interference. So how do you turn, if I know an action, how do I turn an action into a wave function? Well, there was a prescription given to us by Richard Feynman, which is a path integral. And you can see these are somehow elementary path integrals. So you exponentiate your phase and integrate over all paths. So S here, remember that labels all of the rays. It labels in the raindrop, it was the angle at which they entered the raindrop. And we're summing over all of them. So we're somehow including all the, this is a sum over all the classical paths. And we're adding them together with these phases. And when we do that in the case of the simplest one in the hierarchy, the cubic, that gives a function which is well known. It's called the Airy function. So if you ever solve the Schrodinger equation for a linear potential, the solution to that is the Airy function, and that's a plot of its intensity pattern. And so actually Airy, who calculated this in 1838, was doing this in the context of the rainbow. These are called the supernumerary arcs, these interference patterns. You have to look very carefully in the rainbow to see them. If you look below the bow, you can sometimes see the colors repeat. And those repeating colors are these interference patterns. However, as well as some people have heard of the Airy function, almost no one has heard of the Pearcey function, although I know a few people in this audience have, because there's some experts here. But it took about 100 years for people to make the next step. So this is called the Pearcey function. And now we've exponentiated the next one up in this hierarchy. And now we get this interference pattern here. It's a 2-dimensional interference pattern. Here you see the classical caustic, where according to the ray theory it diverges, but now it's smoothed by this universal interference pattern, which is the Pearcey function. And then people sort of cottoned on that there might be a whole hierarchy of these things. This is the next one up. This is an example of a 3-dimensional caustic called the elliptic umbilic. And here you see some slices to it. And we can even make these. So this is I managed to get this on the plane. It's an ordinary glass, okay, but it's covered in bumps. You see, it's supposed to be for a toothbrush. Okay, I bought it off Amazon. You keep a toothbrush in it. So I wanted something that had bad lenses on it. So it's got all these little bumps. You come down and go off. It's not magic or anything. but this is going to randomly focus my light. So if I, let's see, if I do, so this is a fairly round, so you see these nice patterns, and indeed you see the interference that, if I can hold it steady enough, you can see a cusp there with these interference patterns. There's a nice one. So it's just randomly picking these things up. Okay, so you can think of this as it's just this random lensing by these bumps on the side of the glass here. They're bad lenses. You get generically this kind of behavior. Okay, so, and these things are now, they have this, they're like special functions in some sense, but they're if you look at the last chapter in the Digital Library of Mathematical Functions, that's the book form of it, you'll find there's a whole chapter on these integrals, these diffraction integrals, they're sometimes called. And if we zoom in, so the structure on different scales. So if you zoom out of your coffee cup, all you see is this bright line. If you zoom into the wavelength scale, you'll see the interference pattern. And if you zoom in even further, you'll find that there's a network of zeros. They're called dislocations in optics, but they're vortex-anti-vortex pairs in the language of more condensed matter physics. And so these are the finest, they're really even at sub-wavelength scale. And they're the finest structure. So there's 3 levels of structure, for instance, in this cusp. Okay, and another very fascinating thing with them is they obey rules of self-similarity. So each of these structures is associated with a set of scaling indices. So if we take the cusp here, it has these 2 scaling indices, 3/4 and 1/2. That tells you, I go back one, if I change the wavelength of the light, then this interference pattern, if I make the wavelength smaller, the interference pattern gets sucked in towards the cusp point, but it does it, it shrinks with a different scaling exponent in this direction than this direction. That's these 2 scaling exponents. So like many singularities in nature, they're associated with scaling properties. Okay. Actually, WSU has a proud history in these things. So it's not my place to really talk about what work's been done here over the years. But Philip Marston, who I was hoping to meet, but unfortunately is convalescing after an operation. So he's been working on these kind of things for a long time as a real expert, and he's still working on them. And more in the cold atom line than Peter Engel's group. You maybe have heard about this a lot, so it's not my place to say I wouldn't want to get it wrong. But anyway, some of you may recognize these pictures. So these atom lasers dropped from a trap and passing through various past an obstacle made of blue detuned light. In this case, you can get these beautiful patterns. These are now matter waves, not light waves. Okay, so what I've said up till now is well known. Well, okay, is known by a certain, if you talk to the right people, known and loved by a certain group of people. So what have I done on this problem? So I'm trying to introduce the idea of quantum catastrophes. So the motivation here was that the wave interference effects removed the singularities of the classical ray theory. But can there be singularities in the wave theory which are only removed by what we call second quantization? That means, for instance, if we have light, we have the ray theory, then we have the wave theory, and then we have photons. Okay, are there singularities that you can remove that are present in the wave theory, and you need to second quantize to go to photons? So my quanta will actually, most of the examples I'm going to give are ultra cold atoms, so Bose-Einstein condensates and so on, and then the quanta are actually atoms. The fact that you needed the atoms come in lumps of 1 will be my quantum field, if you like. So they're singularities in quantum fields rather than classical fields. And I'll get as far down that list as I can, but I certainly won't get through it. So here's an example. So this is a Bose-Einstein condensate in a double well potential. So that's a sort of spatial picture. You can put the condensate is trapped in these double wells, and there's a tunneling barrier between the two. So these experiments have been done. This is from 2005 from Markus Oberthaler's group in Heidelberg. But what I won't go through it at all, but you can describe a Bose condensate in this double well system in terms of this Hamiltonian. So N here is the number difference between the left and the right well. Okay, so n without a subscript is just the difference. And the phase, phi, that's the phase difference. So these condensates are superfluids, and they can live on both sides. But what is key, the macroscopic variables that describe this, number difference, phase difference, they obey this Hamiltonian. I don't know if this Hamiltonian looks familiar to anyone. If I interpret this number difference as an angular momentum, this would be angular momentum squared, and this would be the potential. Yes, I see someone swinging there. So this is the Hamiltonian for a pendulum. So you can describe this macroscopically as, well, a macroscopic, but still quantum, ultimately a quantum description in terms of a pendulum, where the role of the angular momentum is played by the number difference between the two wells, and the angle of the pendulum is the phase difference. And so if you put a bunch of atoms here, generally they transfer back, they tunnel backwards and forwards, and the pendulum is swinging backwards and forwards. So you can get some equations of motion from this Hamiltonian, and they're actually called Josephson's equations, which come up in superconductivity. This is the equation of motion for the phase difference, and this is the number difference. And you can solve those equations. So imagine we have a situation where we have two Bose-Einstein condensates that have never seen each other before, and I suddenly put them in contact. So if they've never seen each other before, they have no well-defined phase relationship between, they've got random phases, they've never seen each other, but they do have a well-defined number of atoms. The difference, maybe this one has 10,000 and this one has 10,500 atoms. And that's what they know when you first put them together. So this Hamiltonian that I just went through on the last slide doesn't know about the individual, it's not quantized yet. This is a continuous variable, and this is a continuous variable. It doesn't know about the discrete number of atoms. It's what we call a mean field approximation. It's still a quantum system, but it's a classical theory that doesn't know about the individual atoms. When I solve these Josephson equations, each one of them will give a single trajectory. This is a phase difference as a function of time, and this is number difference as a function of time. But if I'm thinking about a quantum theory, I want to go the extra step and ask, what does the quantum field theory say? Well, if I have these two condensates that have never seen each other, and the phase is essentially, and I only have a sense of my number difference, well, then I need to quantize these two variables, or second quantize them. And to a good approximation, they obey the so-called canonical commutator. The phase difference plays a role like position, and the number difference plays a role like momentum. And, well, these are dimensionless, so there's no h bar here, but this would be like xp equals I h bar. So if you have perfectly defined number difference, it means you know nothing about your phase difference according to quantum mechanics. So if we want to describe this quantum mechanically, but we only have the classical theory, the best thing to do is to sum over all the possible phase differences. And so all I've done here is plotted all the solutions to these Josephson equations for all the possible initial phases, and then let them propagate for time. And what you see, well, this pattern I just showed you, generically, I didn't do anything special here. I formed these cusps. But this is now not in real space, not in coordinate space, but either in the phase difference or in the number difference as a function of time. You see they're out of phase with each other, but you get these series of cusps. And it's essentially because this mean field potential, this cos, is a bad lens. Okay, if it was a parabola, if this was a simple harmonic oscillator, down here it would perfectly focus, but it's not. And these focus points explode into these cusps. But we've got a problem here because of this singularity. Okay, we have, if we look at the density of trajectories on this cusp, it diverges. Now, being quantum mechanics, this is probability. So we've got this probability density diverges along these cusps, and that's a problem for me. When I see a divergence, I love to smooth it out. So how do we get rid of that? Well, we're forced, this is one of the examples of a quantum catastrophe, go to the next level of description and pay attention to the fact that this condensate is made up of individual atoms. So we have this double well. We can, to simplest approximation, to say there's two modes, a mode on the left and a mode on the right. And then I need to second quantize, whoops, sorry, too soon. I can have these lowering and raising. I can describe each well as a harmonic oscillator that obeys these commutators. This is for destroying and creating an atom on let's say the left well and destroying, creating an atom on the right well. Now, I won't go through it, but there's a very famous way of mapping from two coupled oscillators onto angular momentum. You take combinations of these annihilation and creation operators for two fields and create out of them angular momenta. So these are spins. So you can think of a two-level system, this two-mode system, as like a little spin. That can be the left, or they can be on the right. And when you add each atom's that way, you add all these little two-level spins together, you get a giant macroscopic spin that is described by these S's, these macroscopic spins. And the natural description of that lives on a phase, essentially because we have two parameters. There's the number difference and phase difference are the two angles on a sphere. This axis here, Sz, is the difference between the number in the left well and the number in the right well, say. So this is a very simple quantum theory, but fully quantum, that pays attention to the atom, the fact that atoms come in lumps of one. So does this solve our problem? Well, okay. The Hamiltonian, our pendulum Hamiltonian, here there's various examples of these two-mode little fields. One is to have, for instance, the transverse field Ising model. So these are spin operators, Pauli spin operators, and they can be in an external field. If you haven't seen this before, don't worry, but you can rewrite it in exactly the form I want in terms of this giant spin squared in the Z. That gives us some nonlinearity. That's due to the interactions between the atoms on each site. That was the angular momentum in this pendulum Hamiltonian, and this is the effect of an external field. But in our problem, we have this double well, or sometimes called a Josephson junction. This is the number difference squared between the two sites, and this gives hopping of atoms or tunneling between the two sites. But this is now a fully bona fide sort of quantum field theory, a second quantized theory. And you can get it with polarization. That's another two-state system. So now let's do the same thing, but solving now for the fully quantum theory. And now my number difference, for example, as a function of time, you can see it's blocky because my atoms come in lumps of one. And so I have these number differences that are discretized. So this is an example of sometimes what's called Fock space, which is the natural space for second quantized systems, quantum many particle systems. And so if I let it run for some particular time and then I do a measurement and I say, oh, what's my number difference? I measure, I count the number, which one can do in an experiment. I will generically get a number. I have to in quantum mechanics. When I ask the quantum system, what's my number difference? It'll tell me an answer, but then I rerun the experiment many times. I get a probability distribution. With my classical theory, I get these caustics with these divergences. But here's second quantizing. I actually regulate the problem. So these are no longer infinite peaks. It's a discretized version. So these are what I call true quantum catastrophes. Okay, and so what we introduce, what is new here from the classical theory is really the discreteness that these are quantum fields.
So
yeah,
if you smooth over what you did, you get the diagram on the top. It looks a little bit different to me.
Well, there is, yeah. So there's interference here. As I let the total number of particles go to infinity, I would begin to reproduce this in the limit. Yeah, I let the number go to infinity. Yeah, so it will return, but there's still interference here. So if I also add some decoherence, which tends to come naturally. Yeah. So these things, then I've sort of really gone to town on these things. So this is this so-called quantum cusp. It lives in Fock space. Maybe in view of time, I won't go too much into the details, but this is a plot of the amplitudes, let's say at a particular time. This is the number difference. Sorry, I've swapped my variable to Z, but it's the number difference normalized to 1. And what's fun when you discretize it is that it can swallow, the discretization can swallow up some of these vortex-anti-vortex pairs, and it sort of has its own morphology in this limit. But okay, maybe we won't worry too much about that. You can do this if you go to the triple well. That was the double well. The triple well, that's the fully quantum theory for the triple well now. That has some interesting things because it's chaotic. Maybe I won't emphasize that now, but now your Fock space is two-dimensional because to define you want to know what's my number difference in these 3 wells, but I have a constraint that the total number of atoms is conserved, they can just hop around, that leaves me really with just 2 parameters. So I now have a 2-parameter control space plus time, and that means I can realize some of the higher catastrophes, but they're the quantum versions of them. So for instance, I can get an elliptic umbilic catastrophe in Fock space. And I can realize this if I start off, so this is my 2-dimensional Fock space. These are the number differences between wells 1, 2, and 3, but in a particular combination that makes the pictures look nicer, basically. If I start off with an initial coherent state where the atoms are roughly speaking, there's an equal probability to find them on the different sites, and then I let the system go, so I switch on the tunneling between the wells, then I generically, in time, I map out, I start off sort of over here, and I go with time. You can see it sort of moves through a sort of focus point. This is the quantum. This is sort of classical theory. Each of these is a mean field trajectory, the classical theory, but the quantum theory, you can't see it here, but is discrete. I think in the next picture we see it better. Yes. In this, so this discretization is not an accident. If you really, you can maybe see the little hexagons in here. This is a slightly different initial condition. This is where we start off. If you start off with a Fock state, a single state, so a well-defined number difference, so rather than the broad distribution in Fock space, but a single point in this number different 2-dimensional number difference space, this 2-dimensional here. This is after a certain time, you find you get these structures appearing naturally. So this one is the hyperbolic umbilic, which was actually the one we, I think this one we saw. Yeah, you see it's a sort of cusp inside this outer band. You see there's a nice cusp, but then surrounded by the smooth. In the very top there, if I can hold my hand steady enough, there at the very top, you see, well, it's at the bottom here, this pattern there. Okay, so those are what I call quantum catastrophes. How are we doing on time? Okay, so you can get, they come up all over the place. They don't have to be in Fock space. These things are in coordinate space, but the quantization here is they're on a lattice. So if you have spins on a lattice and you suddenly flip one of the spins, that information propagates outwards. And you can plot a sort of space-time diagram. So it's a 1-dimensional chain of spins, and this is time. You flip a spin. The information about that spin flip propagates outwards because the spins can speak to each other. It doesn't propagate at the speed of light, so they're not really light cones. It's the speed of the quasi-particles in your system. People can also do this with atoms in optical lattices now, rather than the 2-site lattice, a many-site lattice. If you suddenly change the depth of your lattice, so that's a quench, you suddenly change something, you create a lot of excitations. These caustics are really caustics in the dynamics of this system. But then if you look at this correlation function, for the probabilities to be between different sites, you might see something that looks awfully like an Airy function that was measured. That's experimental. These are experimental results. So we studied these light cones. This is the transverse field Ising model now, not with the infinite range interactions, but just with nearest neighbor interactions, describing a chain. So the chain, this is the spatial part, goes up and down. I'm only showing half of it as a function of time. The edge of this light cone, if you take a cut through it here and you ask, what does the wave function look like? So this information propagates outwards, you get an Airy function. So this Airy function is extremely robust. And here we're verifying the scaling properties to exactly get this 2/3 scaling. So you can formally map. So here's this, remember these wave functions I showed, these catastrophe wave functions or diffraction integrals. You can show from the solution that this is an exactly solvable model, it turns out. You can map these solutions, for example, onto the Airy function. Okay, what else? So this is a problem that I put in because I know Peter's interested in some things. This is some work that my student Liam worked on. So there's, for instance, the quantum dam break problem. So this is, imagine you have a reservoir and it's initially the water is sort of, here's the dam, and if it suddenly breaks, the water is going to flow out. We can do this with a quantum system, a Bose-Einstein condensate, and suddenly release it. Well, there's a few different scenarios you can think of. Here, the equation we're solving is a nonlinear Schrodinger equation. It's nonlinear. The interactions between the atoms. So if it wasn't for this term, it would look like an ordinary Schrodinger equation. But the interactions give rise to this cubic nonlinearity here, which is due to the interactions between the atoms. And if we can think in this, well, there's various scenarios. One is a dry channel where you basically had no water over here to begin with. It flows in. There's also the wet channel where maybe the barrier, you still have some water on this side, but you suddenly remove the barrier. In all of these problems, I'm doing some quench, suddenly removing something. Okay, well, you can do this with, well, at least in our theory, you can do this with a Bose-Einstein condensate. So if you start off with this initial state here, you trap the atoms and you have a barrier which is made of, say, laser light or something like this, and you suddenly remove it. So this is so we can work out, so this one here is very nonlinear where you have the dry channel case. But if you just have a small difference in height, in the density differences between the two, you can do things analytically. So if that's the case, I'll limit myself too. So you just have a small difference, you suddenly remove it, you get these wave fronts that propagate on either side away from this initial density ramp. And lo and behold, what you find, you get these airy functions. Well, they're not quite airy functions. Unfortunately, part of this is blocked by that. But so with this case, you can work it out exactly. In fact, you get an integral of an airy function. But once again, once you do that, you know this airy function has lots of scaling properties, and that describes these ripples that propagate backwards from this step. And if we plot these excitations, this is where the initial dam was as a function of space and time, then you get these nice ripples. Again, you get this light cone, and the edges are in fact caustics, but in terms of these matter waves. Let's keep going. Yes, maybe I have a minute or so to finish. There's another case where these classical waves break down, and that's near event horizons. I won't get to really describe it, but let me at least say the idea. So an event horizon is, near a black hole where light can't escape. And there are analogies to this in ordinary condensed matter, but think of a waterfall. There's a point of no return where the fish can't swim against it. If you have a fluid, and the role of the fish is played by waves, by sound waves, trying to propagate against this fluid. If the fluid is flowing faster than the speed of sound, then there's a point of no return, an event horizon in the fluid. So Bill Unruh was one of the pioneers of this kind of idea. But what happens near an event horizon? You may have heard with black holes, you get redshifting, or it doesn't have to be a black hole. As the light propagates away from an event horizon, it gets redshifted. But if a wave propagates towards an event horizon, the wave number, which is basically 1 over the wavelength, gets smaller and smaller. It gets blue shifted until as you get to the event horizon, you get some kind of singularity. This is the distance from the event horizon. The wave number becomes infinite. In fact, the wave number essentially has no value. So how would we write a wave, a plane wave? You think of e to the I kx, but k now is not constant in space, going with space. So the generalization for just an ordinary plane wave close to the horizon is integral of z dz, z dz. When you have 1 over z, that is going to give you a log. Okay, so what happens is, as you get near an event horizon, your phase undergoes a logarithmic singularity. In other words, your phase has no meaning, which is a big problem because 200 years ago, when people came up with the wave theory of light, phase was the crucial player. And now phase takes all values. It has it's completely undefined at this point. This shouldn't be a surprise to us because actually phase is not a well-defined Hermitian observable in quantum mechanics. I'll just plant that word out there if you want to ask me about it afterwards. But anyway, the result is that your phase becomes undefined. And so this is another example of a quantum caustic, we believe. We have our own theory for this. I maybe won't go through it other than to say it obeys this third order differential equation locally. And in fact, we have a theory describing this event horizon in terms of a bifurcation. So I told you with these Pearcey functions, you get two solutions merging when you cross one of these lines, two classical solutions. If all three of them merge at this point, if you're off center, just two of them merge. And so a cut through this bifurcation here, this cusp catastrophe, two solutions merge. So this is outside the event horizon. This is inside. You generically get three solutions. It looks like a cusp, except when we solve this equation that describes waves near this event horizon, we get this object here, which looks like an Airy function. It's cubic and linear, but we get an extra term, a logarithm. We call this a log Airy. It has properties like a Pearcey function, but it's not quite. It's in fact its own object. We think this log has to do with particle production. So how does nature deal with this phase singularity? In some sense, phase becomes undefined. You're relying on the number variable here, this number difference, the number difference parameter, and that's what gives rise to Hawking radiation. So the way, in my view of things, the way nature deals with this phase singularity, you're forced into a description in terms of the second quantization, and the second quantization of waves near event horizons is what gives Hawking radiation. It excites pairs of particles, and that's all actually within this wave function. What I'm claiming is this is a sort of the universal wave function describing this behavior around event horizon. Anyway, let me finish there. So what have I told you? I've told you that wave dynamics generically leads to caustics. Okay, and close to caustics, you get universal patterns with characteristic scaling exponents. What is the bigger picture for this? Well, I'm very interested in universality. And universality in equilibrium is a well-studied theory. You get universality near phase transitions, which are other examples of singularities. But in dynamics, that's a much newer topic, how to get universality in dynamics. And these are examples of how to get universality in wave dynamics. And we've got various sort of theories proposing that when you go to this second quantization, you get these new types of catastrophes that are associated with the quanta of the fields. Okay, so hopefully when you go out of this room, you'll have your caustic goggles on, and you'll everywhere you look in your coffee cup or at the bottom of the swimming pool, you'll see these kind of objects. Okay, so thank you for your attention.
Thank you so much for this wonderful talk.
Okay.
Time for questions. Up there.
In case of the triple wave,
Yeah.
so let's just assume that the system is isotropic. Is global U1 symmetry still conserved?
Yes, so in the second quantized theory, it is. If I did a mean field theory, so I break U1 symmetry. So when I write down something like this equation here, so this is a classical equation that I have to choose a phase. As soon as I choose a phase of my condensate, then I'm breaking U1 symmetry. But for instance, I mean, the simplest case to talk about is in the double well case. If I have a single trajectory, let's go to the double well case, a single trajectory, and I get there, is each one of these trajectories has at any moment in time a perfectly defined phase, and that's breaking U1 symmetry. So these equations, as soon as I write down this mean field theory, I'm choosing at each moment a phase and a number difference. But if I do the second quantized theory, I don't break that symmetry. And indeed, you can see in some sense, this is my poor man's quantum theory. Before I truly second quantize it, I'm adding up all these different phases. I'm not breaking U1 symmetry there. Is there something within that you wanted to explore, or?
Yeah.
Yeah.
I guess
Okay. Does that answer the question
so,
a little bit? So the triple well is similar but more complicated.
Because the question arose because I didn't see any A1, A2, A3 coupling terms, or that would make sense.
Yeah. So here I'm thinking of pairwise hopping and interaction. So the Hamiltonian in the triple well case here. So these are hopping between the different wells. This annihilates a particle in well 2, creates one in particle 1, and so on, and hopping from 3 to 2, and so on. And then the interactions here are just on each site. So the atoms on each site interact with each other. So there's no 3 particle. You think that would lead somehow to symmetry breaking in particular?
No, I think that won't make physical sense.
Okay, yeah, indeed. It doesn't come up so naturally in this Hamiltonian. Yeah. Okay.
So if you work with the second quantized Hamiltonian, but you assume that your field space is just like a coherent state, then you break the US symmetry, right?
Yeah, if I really have a coherent state. I mean, it's yeah. So some of these states. I mean, this is close to being a coherent state, but it's basically an equal. It's still a. I didn't write down the quantum state here, but it's roughly an equal superposition of all the possible different number differences in this system. So it's close to being a coherent state, but it's still a fully quantum state. Yes, exactly. Yeah.
So in your two-state model,
yeah,
you always, I think in your result, you always start from balance population, right?
You don't have to, actually. I mean, that's part of the point with these catastrophes is they are stable against perturbation. And so it's true just to make nice pictures, I started off with a number different zeros. So that means I imagine putting together 2 condensates that have never seen each other before, but they have equal numbers. And you might say, well, that's a rather special situation. And you'd be right to say that. But that's just, I chose that for simplicity. If you don't do that, just you find this is moved off center a little bit up to here, but you still get this very robust structure appearing. It's just slightly distorted. That's a very important point, actually.
I guess, yeah. Actually, I guess I also want to ask, what's your initial state? Is that like for example, for this one, is that a twin Fock state or is it a coherent state?
It's a Fock state.
It's Fock, like a
yeah.
half.
But it's exactly, so half the particles are in one well, half of them are definitely in one well, the other half are definitely in the other well, whereas a coherent would be a superposition between the two.
What is the type of strands? What's the ratio between the coupling strands with the?
So this is deep in the semi-classical regime where the tunneling is stronger than so this parameter here in this pendulum this is called the so-called charging energy, and this is the tunneling, the Josephson energy. It's deep in the semi-classical regime where the tunneling energy is much larger than so it's a very weakly interacting system. It gives this this is some proxy for sort of some 1 over Planck's constant, basically.
This is oscillating phase. I think it's not in the self-trapping phase.
This is actually, yeah, so it's right on. That's a good question. Is it in the self-trapping phase? I think yes, it's okay. So when you put 2 condensates together and you suddenly whack them together, you actually get that's the point with these quenches, you get a sort of a superposition of excitation of many states, but it turns out the overlap of this initial state is much more strongly overlapped with the so-called plasma oscillations. That's where the pendulum is doing this. The self-trap states are where the pendulum is going one way or the other, and the overlap with that is very small. It's there, but they have a sort of exponentially small overlap with that. So this is mainly, these excitations are mainly a sort of superposition of all the states lying below the separatrix in the Hamiltonian, if that means something. Yeah.
And a question online from Steve.
Yeah.
That you mentioned the coherent states. So the mean field trajectories become complex. You wondered if you could talk a little bit about the complex geometry of singularity.
Yeah, so if I had rays that, maybe let's go to back a picture here. Okay, so you'll see in, for instance, up here, there's regions. Okay, I have a better talk for that. but I don't. Do I have pictures? Yeah. Okay. Give me 1 second. Maybe I do have something to say about that, but I'm going to have to go through a lot of. Yeah. So actually, this is a case where you put together two. You can think of this as two Josephson junctions put together, two wells, but with an unequal number difference. So you start off with some Fock state, unequal number difference, and here you can see you still get these caustics that are just distorted. And if you have these regions here, they're classically forbidden regions where no classical, these are the classical trajectories, this is the quantum. You get regions where no classical trajectories can penetrate. But if you allow complex rays, then you can reach this region and you can get a semi-classical wave function by introducing complex rays in this region. So in fact, this is the dark, each of these is like a rainbow. You'd locally get a nice, I guess online you can't see my, my pointer. And I don't know if you can see my mouse now, but okay, so near these edges here, you get locally an area function here and another area function over here. But this is the dark region. This is, in fact, a very good model for a primary bow and a secondary bow. And in the middle, you get the classically forbidden region, but you can describe the region in the middle there by complex rays. And we have looked at that. Okay, so we have a somewhat unorthodox interpretation of a dynamical phase transition. That's a phase transition as a function of time using exactly these complex rays. Thank you for the question. Yeah.
I'm sure we could go on much longer, but
Yeah.
probably we need to stop here. Duncan is still around for the rest of the day, but he has got a schedule and he'll be here tomorrow too. So if anybody still wants to talk to him, maybe let Michael or Jen know, and maybe they can work into the schedule.
We're stopping the ISM coffee hour tomorrow from
Right.
1 to 4.
Yep, that would be a good opportunity. Thank you.
Okay, thank you. Thank you.